Okay, let's begin. So yeah, as to the question I was just getting, so Wednesday we don't have class.
And Monday we don't have class.
Right, so Wednesday, I think it's a Jewish holiday, and Monday it's just like a general holiday, I think. And so the next time I'll see you guys is like Wednesday, which is
The 19th.
it's far from here. I will be quizzing you on whatever we get covered today. And yeah, another thing that I wanted to remind, you remember this guy? Which we had to do like the product of some forms to figure out. Well, it turned out that was actually a lot harder than it had to be. There's a much easier way. There came a point where we made a decision that brought us down the path where we needed product of some forms, but technically you could have avoided that. I believe, had a student who somehow managed to get integration by parts to work here. I probably wouldn't have recommended that, but hey, if you see it and it works out, that's fine. But still, there's an easier way to do it than the way we actually did it. Like I was going over my notes, I'm like, do we really need product of some formulas here? I mean, in differential equations you would need it, but I don't recall ever needing it in Calc 2, and I'm like, I rewatched the video and I'm like, yeah, we should have done this instead at that point. So try to see if you can find where the path diverged from where it probably should have gone, and I actually try to redo that. Other than that, we're going to pick up where we left off. We're going to finish off these examples. The last example we did was example E. So we're going to pick up from F. We're going to get through the rest of these, and then we'll start the new topic. So. That being said, try to redo better than Jhevon. As it turns out, Jhevon is human, and sometimes he just takes the wrong path. Okay, jumping right back into it. How do we do this? Go. Yeah, F. We did up to E.
Yeah.
The last class ended with example E, so we're picking up from F and continue. Yes?
X equals the tan theta.
Right, that looks like x squared plus a squared, and as you would have done in your quiz, the correct substitution is a tangent theta. So this is x equals 1 tangent theta. Oh, what do we do next? Yeah.
Dx
You need to find the dx. So when you plug this in, what happens?
I roll secant squared theta over tan squared of theta plus 1.
Right, so here we're going to have tan squared theta plus 1, which we know is secant squared. So that's going to give us the secant squared here raised to the 3 over 2. And d theta. Okay, and what's going to happen with that?
So secant squared over secant to the third.
Right, so this will cancel that. And so we have secant squared over secant to the third, which is of course 1 over secant. How do we integrate that?
Cosine.
Right, so that's cosine. Integral of cosine,
Sine.
positive sine, plus c. So that is our answer in thetas. How do we get it back to x's?
Draw the triangle.
Draw the triangle. So we have x equals tan theta. Think of this as x over 1. You know, tangent is opposite over adjacent, so that's x1. That's the square root of x squared plus 1. And so now we just want to know what is sine of theta. Sine by SOHCAHTOA is opposite over hypotenuse. And so this integral is just that guy, x over 1 plus x squared. So that was basically trig sub. So trig sub helps you out when you have situations like x squared minus a squared, x squared plus a squared minus x squared, where your a is considered a constant and your x is some variable, or maybe some amalgamation of a variable, as we saw in some other cases. And yeah, after that, it transforms your integral to a trig integral, which we dealt with in the last section, so you should know how to deal with those. Once you get here, you use the triangle to help you back substitute. Let's move on to G. All right, so how would we do this one?
Is that 2?
This is a 2, yes. From the square root of 3 up to 2. Yes, exactly.
Use substitution. That u equal to x squared minus 3. Oh wait, never mind.
Okay.
X
Alright.
equals something.
I don't know. Never mind.
Okay, otherwise?
X equals something.
No, that's not going to work.
Root of 3.
X equals root of 3. Which trig function do we need? Secant. So our dx is going to be root of 3 derivative of secant. Secant tangent. So, also, changing limits. So, when x equals 2, this means we have 2 equals radical 3 secant theta, which means your secant theta is equal to 2 over radical 3. What theta would give you that?
That confused me totally.
I'm changing the limits. So
60 degrees of cosine.
I want to know what is, this is here is an x equals 2 value, this here is x equals radical 3. I am changing the limits, which means I go back to my substitution equation. You did this in Calc 1 when you want to change the limits on an integer. Go back to your substitution equation, plug in the x value, which is 2, and I want to solve for theta.
5 or 6.
Right, so theta equals 5 or 6. And what about when x equals radical 3? This means you have a radical 3 equals radical 3 secant theta. This means you have secant theta equals 1. This means your theta is? Theta is what? 0. Okay, so that is going to change our integral into so now this would become when x was radical 3, our theta is 0, and when our x is 2, our theta is pi over 6. Our x is radical 3 secant theta, which means when I plug it in there, it's going to be 3 secant squared theta. So that is going to really become 3 tangent squared theta. In the parentheses here, the x is going to be radical 3 secant theta, and my dx is going to be radical 3 secant theta tangent theta. Now, here is, I don't know if to put this in green or red, but if using trig sub with a definite interval, always change the limits. Now, in Calc 1, you're of course taught that you had an option. You could decide to change the limits, or you can do the integration, do the back substitution, and use the old limits. The recommendation is, if you're doing a trig sub, you always want to change the limits. Not necessarily because you're going to get it wrong if you don't change the limits, but it will be much more efficient because you won't have to do that back substitution thing with the triangle. So it'll actually save you time by doing that. So that's just a note I will make there. Now, yeah, question? Moving on, simplify. And this will be radical 3 tangent, so this becomes radical 3 times integral of tangent squared. And yes, of course, I expect you to remember your trig in terms of what special angles give you what special values. Okay, how do you integrate tangent squared?
Tangent minus.
Secant squared of theta minus 1.
Secant squared minus 1 e theta. That's radical 3. Integral of secant squared. Tangent. Integral of 1 theta. And I plug in 0 and pi over 6. So, radical 3. Tangent of pi over 6. What is sine of pi over 6? 1/2. Yes. What is cosine of pi over 6? Radical 3 over 2. You guys need to know that very quickly. So if I take 1/2 divided by radical 3 over 2, what do I get? 1 over radical 3 minus pi over 6. Tangent of 0 is 0. And of course, if you plug in 0 there, that's 0. So that's your answer here. If you don't remember your trig, you need to review trig. It's very important. Very, very, muy important. Including the special angles. If you need to review trig, watch my Math 195 videos. You can go through all of trig in like 4 lectures. H. Ideas? Yeah.
So first, this one is confusing to even say, but if you pull out the negative and then you add 4 inside, you're gonna have positive 4 outside as well because the negative, right? So you're completing this.
Okay, so you want to complete the square inside. So you add 4 and subtract 4, I guess.
Yeah.
That is going to be 1 over the radical of minus. So this part here is going to be x plus 2 all squared. And this here is just going to be minus 4. So that becomes pretty much 4 minus x plus 2 all squared dx. So completing the square was the trick here. And now that you've completed the square, what can you do?
Arc sine of x plus 2 over 2.
You're telling me like the final answer. Give me some.
Turn the 4 into 2 squared.
Okay, and then
You arc sine.
And then what?
You just turn it into arc sine. Or do you have to use sub?
You tell me.
I mean, I think you don't have to really do the whole u sub step here because you have 1 dx and that's going to be the derivative of x plus 2, which I'm assuming is the thing you would take the u sub of. So take the u sub of x plus 2.
That's how you go first?
I mean,
What rule are you thinking?
arc sine.
Yeah, that's specifically, what's the rule?
Oh, the whole thing?
Yeah.
The derivative of 1 over root a squared minus x squared. Or sorry, the integral of that is equal to.
You have this memorized?
Yes.
Okay, and what is
Equal
that?
to arc sine of x over a.
Yeah, that's correct. You can memorize that if you want. There is another one. So, yeah, you have me convinced, but I don't want you to explain for my benefit. You understand? Like when you just jump from there to there, a lot of people aren't going to have this memorized. So I want you to explain to the class. Tell the class how you got that. Yeah. Okay, so I want everyone to understand where this is coming from. Now, either this is a form that you're supposed to remember, so I do expect you to remember this. Now, if you are the kind of person who loves memorizing stuff, I don't know, there are people who like that. I'm not one of them. You could just memorize this as well, But with a little bit of algebraic ingenuity, you could actually figure out that this is going to be the answer anyway. So let's say you remember this. So you get to that point and it reminds you of this. Now you could go through a trig substitution here, x plus 2 equals 2 sine theta. And we'll go through the whole trig sub process and eventually you'll get to it. But another nice way is to actually factor out the 4. So it's going to be a 2 here. And you would have 1 minus x plus 2 all over 2 all squared dx. And then a u substitution of x plus 2 over 2, your du is going to be, of course, 1/2 dx. So your 2 du is going to be dx. And so this guy would now look like the integral of 1 over 2 times the radical of 1 minus u squared dx is going to be 2 du. This is going to cancel. And there's your nice formula. So this, you know, is actually sine inverse of u plus c. I think a couple quizzes I asked you to actually regurgitate that. And then our u is this guy. So my personal preference would be to just factor things out and actually finagle it to look like a formula I already have memorized. I don't like memorizing more formulas than I have to. So. Which, again, also kind of goes to show you, when I do ask you to memorize something, it's because it's important. Because I'm the guy who doesn't like memorizing things, right? So if I tell you, hey, memorize this so that your life is easier, there's a really good reason I'm telling you. Because if my life could be easier without memorizing it, I would have done it. And I'm like, yeah, you don't need to memorize it. Right? So, yeah, that one's a nice one. Another option, again, was to do a trig sub here. It would have been a longer time. So it's nice if you can see the rules here. Moving on to I. All right, how do we do that one? Yeah.
U sub for 4 minus x squared. And then the derivative of that is going to be 2x dx du, and you can sub that for x dx, and you have 1 over root u, or half of 1 over root u.
Yeah, but we're in the trig sub section though. So
That's fair.
why didn't you want to do the trig sub?
I mean, doesn't fit the rule, so.
What doesn't fit the rule?
Because the x is there, that's kind of messing with the whole, what's it called? Arcsine formula.
Right, so you don't see the arcsine formula, but why would you think substitution?
Plus, you gave us steps to follow, so.
That's what I want to hear.
Okay.
Substitution is step 3. So no, Jhevon, I'm not going to go into trig sub because you told us step 3 was to try a substitution. So I thought about that before going right into, x equals 2 sine theta. A substitution is actually the much better option here. In fact, a u squared substitution is even a nicer option. So I'd start there, 2u du is equal to minus 2x dx. So you end up with minus u du is going to be your x dx. So this guy is going to be equal to minus u du, gets rid of the x dx part. This here is just going to, of course, if I plug in u squared under here, it's just going to end up being u. What do we have left? That's it, right? So we have minus the integral du. That's just minus u plus c. Our u was what? It says minus the square root of 4 minus x squared plus c. So yeah, regular substitution. Okay, finally, geez, last example here. J. Okay, how do we do that one?
Substitution.
Substitute what?
So I don't exactly grasp the idea of u squared, so
Okay.
I just subbed u for x squared minus 3, and then you could solve for x squared, which will help in the future.
Yes.
So
Again, substitution. U squared equals x squared minus 3. 2u du is equal to 2x dx. So u du is equal to x dx. From this, we can solve for something that's going to be convenient for later. And that's going to be our x squared is actually equal to u squared plus 3. So of course, what you're going to notice here is that this integral is really x squared times x dx over the square root of x squared minus 3. Now, this guy here is our u, and this guy here is our u du. This guy here is your u squared plus 3. So, we're going to have u squared plus 3 times u du over u. The u's would cancel. Get u squared plus 3. And integral that, u cubed over 3 plus 3u plus c. And our u was the square root of x squared minus 3. So this is x squared minus 3 to the 3 over 2 over 3 plus 3 x squared minus 3. And that's the last one. So, the last two examples, regular substitution was the best way to attack them. Based on the pattern of all the examples, can anyone give me a rule of thumb? When seeing a random integral, when to choose substitution versus trig substitution? What was different about these last two that the others didn't share?
non-constant numerators.
Nope. So that is the name of the game. Trig substitution is one of the more computationally heavy methods out there, so you kind of don't want to do it unless you have to. So really, to trig sub or not to trig sub? Hopefully you picked up on some sort of pattern when we were going through those examples. Anyone else want to take a shot at it? That is the question. What do you think a rule of thumb would be? Yeah.
You could take out an x dx.
Right. You could take out an x dx, but it's a little bit more than that. Because technically, if we had this, we could also take out an x dx. But I would still do trig sub here. So it's not just being able to factor out an x, you can kind of do that in pretty much any case. Yeah?
So the powers of the denominator and the numerator differ by 1 for you to use normal sum?
Right, and you can also, they don't have to differ by 1.
Is it just the top one greater than the bottom?
This here, I would also use regular substitution.
So the numerator's degree is higher than the denominator's degree.
No, I would use a trig substitution for that.
Odd and greater.
Odd power. If you have an odd power of an x elsewhere in your function, a regular substitution is going to work out. Do not use trig sub. you have a factor of an odd power of x, but you know it could be any other variable, x elsewhere. Right? So, trig sum. Not trig sum. Not trig sum. Trig sum. Not trig sum. Get the idea? So, if you can get an odd power, what that means is you'll be able to factor off an x. You'll have an even power left over, which you'll be able to solve for that even power, right? Because any even power, you can think of it as something raised to the 2. So, at this point, if it's x to the 17th, you can write it as x to the 16th times x. Of course, if you do a u substitution, you'd be able to solve for x to the 16th, or this be 4 minus u, or u squared if you want. You could actually raise both sides to like the 8 to get that x to the 16th, right? And of course, binomial theorem is something else you guys know, so multiplying it, you'll never actually get something with that larger power in practice in Calc 2. But you know how to multiply that out using Pascal's triangle or binomial theorem, which you also learned in calculus. So if you forgot that, you can look it up. So yeah, in these situations, I would not use a trig substitution. A regular substitution is going to work. So just because you see the a squared minus x squared form doesn't mean you mindlessly jump into trig substitution. It can be more annoying, more trouble than it's worth. Just see if there's an odd power elsewhere. If there isn't, then if it's an even power elsewhere, including x to the 0, 0 is even. So if I had 1 over this, I would do a trig sub. Yeah, otherwise, yeah, that's how we do it. So, last two examples. Didn't regular substitution work? Okay, let's introduce the next topic. We are going to move on. Did a bunch of examples for trig sub. Hopefully that kind of made it sunk in for you guys. If not, there's always tutoring. And of course doing your homework. So we're moving on to 8.5, and we're going to skip 8.6, but now we're going to start 8.5, which is the material that was on the bonus column to the quiz. So let's actually look at what that is. It's integration by partial fractions. That is the next thing we're going to talk about. So it's another integration technique. I think after this one I have one more integration technique to tell you. So that's going to bring us up to like 7 techniques or something. So let's do a motivating example. Suppose I had to do the integral of 1 over x squared minus 5x plus 6. Now, based on what we've known so far, what are my options here? It's not a basic rule, can't simplify it to be a basic rule. I would obviously think substitution, but if I do u equals the denominator, I'm going to get a 2x minus 5. And how am I going to squeeze that out of there? One thing, knowing what we know so far, that we could have done here is complete the square in the denominator. With what we know so far. Best approach is probably to do this. I would complete the square. So what is that going to look like? That's going to look like x minus 5 over 2 all squared. If I square 5 over 2, I get 25 over 4. And I need to get to 6. So what is 6 minus 25 over 4?
1 over 4.
Is it?
Yeah.
So it's going to be 1 over 4 plus? minus 1 over 4, which I can think of as minus a half squared, and then you would do a trig sum. So x minus 5 over 2 is going to be equal to 1/2. What trig function goes there? Right? Which at this point, you're probably already thinking, yuck. There has to be a better way, Jhevon. Tell me there's a better way. There is a better way. Okay. So, here's a situation where I don't really care to use trig sub because, come on, the fractions and everything. Then I'm going to have to back substitute, draw a triangle with all those weird fractions, and okay, kind of annoying. Now, no offense if trig sub is your jam, but I probably don't want to do it unless I have to. So, here's a better way to approach that. Note, this integral here is actually the same as this integral here. And you can check. If you combine these two fractions here, you'll get that one. This times that, you get x minus 2. This times that, you get 3 minus x. The x's cancel, so you'd end up with 1 on top. And if you multiply the denominators, it actually multiplies out to this guy. So it turns out that this fraction is actually equal to the sum of these fractions. Now for these guys, they're actually super easy to integrate. You have formulas memorized that can deal with this. ln of x minus 3 minus ln of x minus 2. Of course, technically there's a u substitution that happens in here, but your du is going to be equal to dx, so you don't really have anything happening. So it turns out that this guy is that guy, and so this is the answer to that integral. And that's what's called integrating via partial fractions. So everyone got it? Okay, great. Let's move on to the next section. How did I do that? Right? You just typed it into Wolfram Alpha. Well, yeah, but I didn't have to. That's the important thing. It turns out that there is actually a process that can help you go from this stage to that stage. Of course, there are certain things that you need to have in place in order to do that, but that is the goal of this section. I'm going to teach you how to do something like this. How can I know when a fraction will break up into a bunch of smaller fractions that are easier to deal with, and then how can I actually go from this situation to that situation? And that is the topic of 8.5. So this guy here, this is called, this here, these are called the partial fractions of the guy over here. Right? So if you have a sum of smaller fractions that add up to some larger fraction, the smaller fractions are called the partial fractions of the original. And the process to go from, this situation to that situation is called partial fraction decomposition. Right? So you can use the partial fraction decomposition to actually write this guy as a sum of partial fractions. The idea, of course, being, which as you can see is convenient, idea, you can break up some fraction into its partial fractions. And the idea is these guys are easier to deal with. That's the whole kind of premise of this entire chapter. If I'm given some large rational function, can I write it as a bunch of smaller rational functions that I can deal with a lot easier? And the answer is sometimes yes. I'm going to tell you when that can happen, and I'm also going to tell you how to actually accomplish this. How do you actually do it? How can you go from here to here without Wolfram Alpha helping you out? Right? Which, by the way, you could literally type partial fractions of, type this, and Wolfram Alpha is going to spit that out. So you can even make up your own problems and actually use Wolfram Alpha to check. Wolfram Alpha does know how to find partial fraction. Okay, so let's get into how we would accomplish this. So first, some partial fractions. The how-to. Okay. So notice here we have to be given a rational function. So it has to be a rational function. Now remember what rational means, it's just the ratio of two polynomials. Which is proper. What proper means is that the degree of the numerator is smaller than the degree of the denominator. Okay, so you have a rational function. You notice that the highest power on top is smaller than the highest power on the bottom. And so a lot of requirements here. The denominator factors. Now, for those of you who are eventually going to take complex analysis, you can like factor it all into linear factors all the time. Every polynomial will factor. Every nth degree polynomial is going to factor into n linear factors up to multiplicity. But of course, we're in Calc 2, and you probably don't know about complex numbers yet, so over the rationals. So pretty much the kind of guys you saw that we asked you to factor in pre-calc. Those are the same guys that we're talking about here. So you should be able to look at the denominator and tell that it factors. For example, x squared minus 5x plus 6. That actually factors into x minus 3 times x minus 2. Right? So you have to notice that the denominator can factor. Then we can do a partial fraction. So under this scenario, we can actually do something like what I did here. You have a rational function, the degree on the top is smaller than the degree on the bottom, and the bottom actually factors. Whenever you're in that situation, you can do something like this. How do we do it? Step 1. Okay, so first of all, you can actually start doing this with general rational functions, but step 2 is to make sure it is proper before you even start to do anything. So pretty much notice whether what the highest powers are, and if it's not proper, it's not like all bets are off. You can actually just simplify it. Make it proper. Via algebraic manipulation, which I'll show you some examples. So that means like multiplying, dividing by something convenient, or factoring it in a convenient way or something like that to cancel stuff. Algebraic manipulation or long division, polynomial long division. So I'm going to go through some examples of this. But of course, this is again a topic done in pre-calc, so I'm just going to do one quick example just to jog your memory. But if you don't remember, go watch my Math 195 lectures and remind yourself about polynomial long division. You're also going to need to know how to factor stuff, so you'll remember all the factoring techniques, including the rational roots theorem. Go back and watch my Math 195 lectures. So let's actually deal with step 1 though. Let's say we're in a situation where we are not proper. What can we do? So here's an example. So this is going to be similar to one of the examples that you saw in the quiz. Let's say we had x squared plus 1 over x squared plus 2. Okay. So notice that that is not proper. The degree of the top is the same as the degree of the bottom, right? So it's not smaller. So one thing you can do here is a common technique. Get the denominator in the top and make corrections for it. So here's what I mean. So we have this fraction. It's not proper. How can I turn it into something proper? Well, I'm going to get the denominator in the top. So what I'm going to do is I'm going to make sure I'm going to just put an x squared plus 2 in the top. Because, you know, this is math, we can just put it in. Right? So over x squared plus 2. But of course, the original is not x plus 2. So if I just put in an x squared plus 2, I have to make a correction for this to give me back the original. What would the correction be? Minus 1. Right? So I just cleverly thought of plus 1 as positive 2 minus 1. That allows me to get the denominator in the top. Right? So I put the denominator in the top and then I make corrections. I add and subtract stuff to get it back to the original numerator. Now what do you think I can do here?
1 minus 1 over x squared.
Right. At this point I can divide this into 2 fractions. So it's going to be 1 minus 1 over x squared plus 2. So notice that now that's a proper fraction. Right? The numerator has a smaller degree than the denominator. Right? And yeah, you can do things like this whenever convenient. So very similar examples, if you have this, for example. What you could have done is first factor out an x. Then you can do the same thing. This is x times x. This is x times x squared plus 2 minus 1 over x squared plus 2. And I can split that up then into x minus x over x squared plus 2. So again, I can make it proper, right, by doing some sort of algebraic manipulation. So one of the easiest ways to get this done is to put the denominator in the numerator and make corrections. You need to make sure that it actually will, if you actually multiply this out, you'll get the original. So that's, you don't want to change the value of anything. So that's one option. Another option is long division. So polynomial long division is another option. This is equivalent to synthetic division, but long division is superior to synthetic division because long division can deal with cases that synthetic division can't, as well as I can never remember how to do synthetic division. To be honest with you, that's the little table thing and blah blah blah. But the thing is, if you're not dividing by a linear factor, you're kind of screwed with synthetic division. It only works if you're dividing by a linear factor. So why learn it if it only works in like a couple situations? Polynomial long division. This is something that will work in general. So here is how it goes. Right? So you want to do we're going to do the same example so you can see that I would actually get the same answer. So you have something like that. The guy that's under here, that's called the divisor. You put that guy out here. And the guy that's on top, you're going to put under here with one caveat. You need to account for all powers counting down. So you start from the highest power. Notice that there's no x to the 1, so you kind of have to artificially put it in there. 0x. and then plus 1. So you throw in your polynomial, the guy that goes under the stick has to account for all powers counting down. Because you're going to need things to line up in a certain way. So if you squish everything in, it's not going to line up correctly, you're going to end up getting confused. So you take the first guy here into the first guy there. X squared divided into x squared goes 1. You're going to take that 1, you're going to multiply these two guys, and you're going to put the result underneath. 1 times x squared is x squared. 1 times positive 2 is, want to make sure things are lining up, so I put the positive 2 over here. And you're going to subtract this line from the line above. The x squareds will die, and then you have plus 1 minus 2, and that leaves you with minus 1. Now what you'll notice is that minus 1 is a smaller power of x than x squared is, so at this point you stop. This is the guy that's called the remainder. And so at this point you actually stop. This guy here, you probably don't need to know this, it's called the ocean. This guy over here is called the divisor. And so now, once you see that, the answer is going to be the quotient plus the remainder over the divisor. That's how you write the answer. So that is going to be 1 plus the remainder, which is minus 1, over the divisor, which is x squared plus 1. And you'll notice that I got back the same answer. So that's polynomial long division. And if you don't know this, you're not going to learn from the example I just did. But it is something that you cover in pre-calc, so if you don't know this, go watch my Math 195 lectures. I explain this at length, do tons of examples. But I'm going to move on because I'm assuming that we're all good at pre-calc here. Yeah?
Not with that, but with that. How did you jump from the factored form to the, my algebra?
Oh, the same idea. I just split the fractions up. So this I can think of as x times x plus 2 over x squared plus 2 minus x times 1 over x squared plus 2. I split the fraction across these two parts here. So the algebraic manipulation is going to be a lot cleaner whenever it can work out, but if you don't see it, it is something that you kind of have to see and know how to finagle things. That's especially a skill that's going to be helpful in differential equations for those of you who have to take it. But if you can't really see how to do that, long division is always going to be an option. It's a lot more systematic, a lot more algorithmic. If you learn this, you'll never be at a loss for anything. If you don't see that way, this way is always going to work to actually break down the powers. So yeah. So that is step 1. Notice, is it proper? If it's not proper, make it proper by actually dividing that thing out. Once you can do that, this brings us to step 2. Now, of course, I do recommend that afterwards, after this lecture, you're going to go home and you're going to copy all the steps down, like on a clean sheet of paper, one after the other. Because I'll be doing examples at each step so you can see what I'm talking about as I'm talking about it. But that's going to make you, like, the notes are going to be forever. Right? You really want to go and write down all the steps in by themselves eventually. So, step 2. Except this one. I probably won't do any exams for this one because step 2 would be to factor the denominator. Now again, I guess I have to say fully factor the denominator because some people just, okay. Fully factor the denominator. And I expect you to remember all your factoring rules, techniques. Including using the rational roots theorem. So remember all your factorization techniques, special factors, the AC method, factor by grouping, all of that stuff, you need to remember it, you need to be good at it. Also, you need to know how to use the rational roots theorem. If one of these methods, one of the regular factoring technique methods doesn't seem to work, you could try to see if the rational roots theorem can get you a nice factoring of the denominator. And yeah, you basically move on with that. That's all I'm going to say about step 2. So, if you know you don't know about factoring, or you don't remember what the rational roots theorem is, what am I going to say? Watch my Math 195 lectures. Right? This is Calc 2. Right? It's not a pre-calc class. I'm not going to teach you about this again. I talk about things like this at length in my pre-calc lectures, so that's on you to learn it. Okay. Yes. Did someone say something? Step 3. Okay. So, step 1, make sure it's proper. If it's not proper, use long division or algebraic manipulation to get it to be proper. Step 2, you're going to factor the denominator completely. Step 3, you're going to break into smaller fractions whose denominators are each of the factors in step 2. The numerator, so the denominators are just going to be, all these factors that you got from step 2, they're going to be in the denominators of the thing that you break up. The numerators are generic polynomials of 1, specifically 1 degree less. Just hold that. Than the denominator. Okay, what the hell are you talking about, Jhevon? Okay, so here's an example. I'll give you a few examples. So let's say I had something that seems to break down like this, x times x plus 1, right? What I would do is I would actually break that up into 2 fractions, because there are 2 factors. It's going to break up into one thing where the denominator is x, the other thing where the denominator is x plus 1. The degree of the denominator is 1, which means the degree of the numerator needs to be 1 degree less. If you have a linear function, the degree is 1. 1 degree less would mean degree 0, which means a constant should be up here. Now you don't know in advance what that constant is going to be, so you just put some generic letter. That's going to be some arbitrary constant. Same thing here, that's going to be some b. So we don't know what the a and b's are yet. We are going to find them in further steps, in step 4. But in step 3, the first step is to actually factor the denominator and break it up once it's actually proper. So, as far as the Calc 2 student is concerned, that is fully factored. If you're in complex analysis, it's not. We don't do complex analysis. How does this break up according to that rule? Yeah.
A over x plus bx plus c over x.
Right? Denominator factors, fully. The factors are x and x squared plus 1, so I break up 2 fractions with x and x squared plus 1. What goes on top is always 1 degree less than what's on bottom. First degree here, you need 0 degree up there. Here, you have a second degree thing in the denominator, which means you need a first degree thing in the numerator, right? Which makes it a linear. Now you want to have a full linear thing, a full generic, that's what generic kind of means. So you account for all powers counting down, but the highest power should be 1 degree less than the numerator. Similarly, if I were to have something like, well, you guys would know how to factor x cubed plus 1, but let's say x cubed plus 7. that wouldn't really factor on the rationals, right? You can factor that with a square. Think of it as the cube root of 7 cubed, but whatever. This would break up into Are we getting the idea?
Yeah.
Okay. So you factor the denominator. You break it into smaller fractions where each factor of the denominator is its own denominator in its own fraction. What's on top is a generic polynomial 1 degree less than what's in the denominator. So if there's a cubic in the denominator, you need a quadratic on top. If there's a fourth power here, you'll need a third power polynomial there, etc. Right? Always 1 degree less, specifically. It has to be 1 degree less. Now, there is a caveat to step 3 that will help us break things down further. So technically this isn't a step 4, I'll think of this as step 3. Right? If there are repeated factors, you must have repeated fractions. It's not really a nice way to say this, I would say counting up to the multiplicity. What I mean by counting up to the multiplicity, here's an example. A repeated factor just means when you factor it, you have the same factor appearing more than once. So, for example, let's say I didn't have x times x plus 1, I had x times x plus 1 squared, right? So the x plus 1 factor is repeated. So what we do is we actually break up the fraction with the x squared, x plus 1 into further fractions, where we count up to the multiplicity, meaning I would break this up into a over x plus b over x plus 1 plus c over x plus 1 squared. Count up to the multiplicity. If I had that was a cubic, I would have a over x plus b over x plus 1 plus c over x plus 1 squared plus d over x plus 1 cubed. Getting the idea? Yes.
So we multiply the power, like when you split it.
Yeah, you start at 1 and count up to the power of 3. Right? And this needs to work, of course, in conjunction with the previous step. So if I had 1 over x times x squared plus 1 squared, the x squared plus 1 is repeated. So the factor is x squared plus 1. I would break this up into a over x plus bx plus c over x squared plus 1 plus bx plus e over x squared plus 1 squared. Right? So I'm still following the rule that I'm 1 degree less than the main factor in the denominator. Right? And of course here, you go by the factor that's repeated. So I think of this as a quadratic, not as a 4th degree. Now, you're probably wondering why is that? No, I wasn't actually wondering why that is. I don't take your word for it. I don't care. Okay, but the idea is if you apply step 3 in a situation where you have something like this, what would happen is because there's a square in the denominator, technically you want a linear thing in the numerator. So what you would have done, the nicer way to get the linear thing is to think of your x plus 1 as the variable. And so technically you put a x plus 1 plus b in the top. right? But it turns out that you'll be able to split this ax plus 1 over x plus 1 squared plus b over x plus 1 squared, which of course this cancels that, so you get the a over x plus 1 plus the b over x plus 1 squared. So that's why the numerator follows what's going on the inside factor. It's just a very convenient way to break down a fraction like this even further. So the smaller we can get the pieces, the easier our life is going to be at the end. So that's the caveat to step 3. If you have a repeated factor, you have to repeat that fraction until you count up to the highest power. It's called counting up to multiplicity. So that would be step 3. Now, of course, in step 4, you are going to need to find what these numbers are, the a and the b. Right? So eventually, you want to be able to find the a and the b. So step 4. What you're going to do in step 4 is find the values of the arbitrary constants. Two main methods to do this. Method 1. Let's say we had that was the guy that we started with. Let's actually see how I figured out that that was 1 over x minus 3 minus 1 over x minus 2. So the first thing you were to do is, of course, you would factor the denominator because it's already proper. Second thing you would do is you would break this up. And with your generic numerators. Okay, so step 1 of the method. Multiply both sides. By denominator on the left. So I'm going to take both sides and I'm going to multiply by the old denominator, which, as you can see, if I just write this down again, it's easier to look at it in factored form. So essentially I'm going to multiply both sides by x minus 3 times x minus 2. What is going to happen is, on this side, the denominator is going to cancel. On that side, the x minus 3's are going to cancel. I'm going to be left with a times x minus 2. And on this one, the x minus 2's are going to cancel. And I'm going to be left with b times x minus 3. That's the first step. Multiply both sides by the main denominator. Okay. The second thing you're going to do, so that's step 1. Second thing, plug in convenient values for x. This is an equation. It works for all values of x. Now, this won't always be possible, but whenever possible, the most convenient values that you can pick are the values that are going to wipe out all of the arbitrary constants except one of them. So, in this case, can you tell me something that would be convenient? X equals 3 is convenient. Why x equals 3 is convenient? Because if I plug in x equals 3, the b cancels. That goes to 0. I would then have a equals 1. Another convenient value? 2. Plug in x equals 2. That's 1 equals, now the a is going to cancel because that's 2 minus 2, so that goes away. Plus b, I have 2 minus 3. So I get b equal to negative 1. Therefore, Now, these are my partial fractions, and we just computed that our A is 1, and our B is -1. Those are the partial fractions, yeah.
Is there any particular way you would order the factors?
No, doesn't matter.
Like, there's no difference between x minus 3 and x minus 2 being on the left or right?
Yeah, no. You'd still have gotten a -1 if there was an x minus 2 here, and a plus would be there. I wrote it that way because it's kind of weird to have the negative in front, but you'd get the right coefficient either way. So that's method 1. Method 2. So you bring it to where method 1 would be in step 1. So we have the x squared minus 5x plus 6 equals a over this plus b over that. And so step 1, same as previous method. So we're going to actually multiply both sides by the denominator on the left. Now, step 2 in this method is you're not going to plug in convenient values, you can actually multiply out. Multiply out the right side, combine like terms. So what we can do here, this will be ax minus 2a plus bx minus 3b and then combine like terms. So that's a plus b x minus 2a minus 3b. And so, to finish this off, you're going to equate like powers and solve simultaneously. So you have to remember how to do simultaneous equations. So what does that mean? Notice on the left side here, I have 0 x's plus 1 equals a plus bx plus minus 2a minus 3b. I'm going to equate like powers. So the number of x's on this side have to be the same as the number of x's on that side because it's an equation. So my a plus b must be equal to 0. Similarly, the constant on this side must be the same as the constant on that side because it's an equation. So this whole expression must be equal to 1. So now what you'll realize is you'll be able to get a set of simultaneous equations here. So you pretty much have a plus b equals 0 and minus 2a minus 3b equals 1. Multitude of ways you can solve this. So I know that a equals minus b, so I can plug this in. And here I've got 2b minus 3b equals 1, so I get b equals minus 1. And so, of course, if a is minus b, that would mean a equals plus 1. And we get the same guy. Those are the two main methods. And we'll end there. So, next lecture I'll actually give you a third method that works sometimes. It's a shortcut. It's called the cover-up method. So we'll talk about that, it's pretty cool. And then we're going to do a bunch of examples where I'm going to have you guys do partial fractions. In the meantime, you can actually go home and make up some problems. Right, so I can just x plus 1 plus 3 over x plus 7. Combine them and try to get those guys back with partial fractions. So you can do a lot of practice with that. But we will stop there. That's partial fractions.
Professor, are we
Yes.
ever going to use this in